Okay, let's dive straight in. Think about this. Everything around you, the very air you're breathing right now to the device you're holding,
Yeah.
even you yourself, it's all made of unbelievably tiny moving parts.
It's fascinating, isn't it? And it's not even a new idea, really. People have been wondering about the fundamental building blocks of our world for centuries.
Exactly.
And in this deep dive, we're going to look at some of those early thoughts alongside our modern scientific understanding, which often gets called the kinetic theory of matter.
Right. We've gathered some really interesting material that looks at how different cultures and, brilliant minds tried to answer this basic question. What is matter?
Yeah.
So for you tuning in, our aim today is basically to unpack these ideas without getting too bogged down in heavy science speak. We want to uncover some surprising things about what makes up our universe, how those tiny bits behave, and the forces between them.
We're talking about the principles that explain, how some bugs can just walk on water or why your coffee cools down. Everyday stuff, really.
Totally. So where do these first ideas about matter even come from? Our sources point some really interesting early views.
Well, the ancient Greeks, for example, they believed everything was a mix of four basic elements: fire, water, air, and earth.
Okay.
They figured the specific properties of anything came from the ratio of these elements, almost like a recipe.
It's interesting they picked those four.
Yeah.
I mean, our fire and air may be more like energy or states than actual stuff like earth and water. What were they seeing, you think?
That's a good question. Maybe phase changes or visible effects.
Could be. And it's also striking that a similar idea, though slightly different, popped up in ancient India.
Right. They had five elements: Akash, which is often seen as space or ether, plus Tejas, fire, Ap, water, Vayu, air, and Kshiti, earth.
So some overlap, but with that extra one, Akash, in their fundamental set.
Yeah, but what's really quite amazing from the Indian perspective is the insight of Rishi Canada.
Ah, yes, him.
Centuries before we had microscopes or anything, he proposed this idea of Anu, basically translating to atom.
Wow.
The idea that all matter, didn't matter if it was solid, liquid, or gas, is made of these incredibly small, fundamental particles. That's a pretty huge leap for back then.
It really is.
Yeah.
So these early thinkers were grappling with the basic nature of reality. Now let's jump forward centuries. Science gives us tools to look at this much more closely, leading to the kinetic theory. You can sort of see this thread of curiosity, can't you?
Definitely. A continuous effort to figure it all out.
So we've got these historical ideas setting the stage. Now let's get a bit more formal, scientifically speaking. What exactly is matter, according to science?
Well, simply put, matter is just anything that occupies space and has mass. Pretty broad.
Okay, takes up space, has mass. Got it.
And matter itself is made of elements. An element is a fundamental kind of matter that you can't break down into simpler stuff by normal chemical or physical means.
Like gold
Yeah.
or oxygen. You can't really break those down further chemically.
Exactly. Those are elements. They're the basic ingredients.
Okay, so all the stuff is matter. The fundamental types of stuff are elements. And each element has its own unique kind of atom. So what's the smallest piece of an element then? That's the atom, isn't it?
Precisely. An atom is the smallest unit of an element that can take part in a chemical reaction.
Okay.
Now, here's a key point from the source material. An atom might exist on its own, or it might not. Like, a helium atom is fine by itself, but an oxygen atom, it usually needs to buddy up with another oxygen atom to be stable.
Ah, which leads us nicely to molecules. The source says a molecule is the smallest unit of matter that can exist independently.
That's right.
So it's formed when two or more atoms join up. Could be the same element, like your oxygen example, O, or different elements, like water, HO. Two hydrogens, one oxygen, all linked together.
And the crucial part is that these molecules still have all the physical and chemical properties of that substance. A water molecule, well, it behaves like water.
Right. Now, these atoms and molecules, they're incredibly tiny. We can't see them. So how do we actually know they're there and, constantly moving?
This is where the kinetic theory of matter gets really interesting and provides some solid evidence.
Okay.
Think about dropping, say, a tiny bit of ink into a glass of water. You see it spread out, right? Slowly, the whole glass gets colored.
Yeah, it doesn't just sit there in a blob.
Exactly.
Yeah.
That's because the tiny ink particles are constantly moving, bumping into the water molecules, mixing everything up on a microscopic level until we see the result.
And it's the same when you dissolve sugar in water. It seems to vanish, but really the sugar molecules are just spreading out among the water molecules.
Precisely. They're dispersing, interacting. And another classic one you've probably experienced, perfume.
Oh, yeah. Open a bottle in one corner.
And soon you smell it across the room. The perfume molecules are moving, spreading out, mixing with the constantly moving air molecules. All these everyday things point to what we call the kinetic motion of molecules.
So this perpetual motion, this constant jiggling at the molecular level, that's a core part of the kinetic theory. What else does the theory say about these tiny, energetic bits of matter?
Well, first, it states that all molecules are always in continuous random motion, and because they're moving, they possess kinetic energy. That's the energy of motion.
Okay, makes sense. Moving equals energy.
Second, this kinetic energy is directly tied to temperature. Heat something up, the molecules move faster, more kinetic energy. Cool it down, they slow down.
Right, right. Hot things feel more energetic because their molecules are literally more energetic, moving faster. What about how they interact? Are they just bouncing around totally independently?
Not entirely. The theory also proposes that molecules attract each other, at least to some extent. There's an attractive force. When it's between molecules of the same type, we call it the force of cohesion. It's what holds the substance together.
Cohesion, like cohesive, sticking together.
Exactly. And this force is strongest in solids, which makes sense why they're solid, right? It's weaker in liquids and really, really weak in gases.
Okay, so cohesion is like molecules sticking to their own kind. What if you have different kinds of molecules meeting?
Ah, that's where the force of adhesion comes in. Adhesion is the attraction between different types of molecules.
Examples.
The source gives good ones, like water droplets clinging to a glass. That's adhesion between water and glass molecules.
Oh, okay.
Or chalk marking a blackboard. That's adhesion between the chalk particles and the board's surface.
Gotcha. So cohesion is like attract, like adhesion is different things attract.
Yeah.
And these forces, cohesion and adhesion, they're both types of intermolecular forces, right? The stickiness between molecules.
Precisely. And between these molecules, there's space. We call that intermolecular space. And there's a really important link here. The smaller the intermolecular space, the stronger the attractive force.
Ah, okay. So less space means more pull.
That's why solids, where molecules are packed super close with tiny spaces, have the strongest forces holding them together.
This is really building a picture. Let's use this to look in the different states of matter. Solids, liquids, gases. How do these arrangements and forces play out?
Okay, let's start with solids. As we said, molecules are packed very tightly, very small intermolecular spaces. So because they're so close, the intermolecular forces, mainly cohesion here, are very strong. They hold the molecules pretty much in fixed positions.
But they can still vibrate, right?
Oh, yes, they still vibrate.
Okay.
But they don't really move around from their spot. This tight, ordered structure is why solids have a definite shape, a definite volume, and why they're generally rigid and hard.
Right, like a tiny, organized crystal structure almost. Okay, what happens if we add heat, add energy, and break some of those bonds to get a liquid?
Well, in liquids, the molecules are still quite close, but not as tightly packed as solids. The intermolecular spaces are bigger.
Okay.
This means the intermolecular forces are weaker. They're still there, but the molecules have enough energy to move around more, to slide past each other.
So they can flow.
Exactly. They're still attracted enough to stick together and maintain a definite volume. You know, a liter of water is still a liter. But they don't have a fixed shape. They take the shape of the container.
More freedom to roam, but still connected. Okay, and then gases. Sounds like a whole different ballgame.
It really is.
Yeah.
In gases, the intermolecular forces are incredibly weak, almost negligible sometimes, and the spaces between molecules are huge, much, much larger than the molecules themselves.
Right.
So gas molecules basically move around independently, bouncing off each other, and the container walls spreading out to fill the entire container.
No fixed shape, no fixed volume.
None at all. It's all down to that weak attraction and large separation.
Okay, so the packing and the forces are the keys to solid, liquid, gas. Now, the source material also talks about some really cool things that come from these interactions, like surface tension. What's that about?
Surface tension is, it's a really neat property of liquids. It's this tendency for the liquid surface, the part open to the air, say, to act like it's a stretched elastic skin.
Like a membrane.
Exactly, like a stretched membrane that's always trying to contract and make the surface area as small as possible.
So that's why water droplets try to be spherical, because a sphere has the smallest surface area for its volume.
Precisely. And it's kind of mind-bending that this visible property comes from just how those tiny invisible molecules are pulling on each other underneath.
Yeah, those perfect beads of water on a wax car. What actually causes this stretched skin effect at the molecular level?
It goes back to those cohesive forces. Imagine a molecule deep inside the liquid. It's being pulled equally in all directions by its neighbors, right? So the net force is zero.
Okay, balanced out.
But a molecule right at the surface, it only has neighbors below and beside it. There's nothing pulling it upwards from the air side, really.
Ah, so it's an unbalanced pull.
Exactly. There's a net inward pull from the molecules below. This pulls all the surface molecules closer together and inwards, causing the surface to tighten up and contract.
Like they're all holding hands and pulling inwards.
Creating tension.
Really? Okay.
Yeah.
And the source mentioned a difference between surface tension, liquid gas, and interface tension.
Right. Subtle point. Surface tension is usually liquid air or liquid gas. Interface tension is the tension at the boundary between two different liquids like oil and water. Same idea, different interface.
Got it. And water has a particularly high surface tension, doesn't it?
It does, compared to many other liquids. Interestingly, dissolving stuff in water often lowers the surface tension, though some salts are exceptions. Temperature matters too. Hotter liquids generally have lower surface tension.
Right.
Even electrical conditions can apparently affect it.
And we see this everywhere. The
Yeah.
source had great examples, like those insects that can walk on water.
Yeah. Their weight is spread out enough that they don't break through that surface skin.
Or carefully floating a needle on water, even though steel is way denser.
That's another classic one. And think about soaps and detergents. Their whole job is basically to lower water's surface tension.
Why? How does that help cleaning?
Well, lower surface tension means the water can spread out more easily, wet things better, get into the tiny spaces in fabrics, and lift away dirt and grease.
Makes sense.
Yeah.
The source even said hot water cleans better, partly because of its lower surface tension. But detergents can kind of do the same job, even if the water isn't hot.
Yeah, that was a neat little tidbit. And there are practical uses, like that clinical test for jaundice bile in urine lowers its surface tension, apparently.
Wow, who knew?
Right. And the advice about not touching the inside of a wet tent.
Yeah, why not?
Because you can break the surface tension holding the water droplets in the weave of the fabric, letting the water leak through.
Huh. Okay. And rainwater beating up on wax. That's cohesion being stronger than adhesion.
Exactly. The water molecules stick to each other, cohesion, more strongly than they stick to the wax, adhesion, so they pull into drops to minimize contact with the wax.
And oil and water not mixing. That's interface tension.
Yep. High interface tension between them. They just don't attract each other much.
It's amazing how these everyday things all link back to molecular forces. Okay, another term for the material. Meniscus. What's that curve?
Ah, the meniscus. When you put a liquid in a narrow container, like a test tube or a measuring cylinder, the surface right near the edge often isn't flat. It curves.
Right, sometimes it dips down, sometimes it bulges up.
That curve is the meniscus, a concave meniscus where it dips down in the middle, like water in glass happens when adhesion is stronger than cohesion. Meaning the water molecules are more attracted to the glass walls than they are to each other, so they kind of creep up the sides a bit.
Okay, I can picture that.
Yeah.
And the opposite, a convex meniscus, bulging upwards, like mercury in glass.
Precisely. That happens when cohesion is stronger than adhesion. The mercury atoms are much more attracted to each other than to the glass, so they pull inwards, minimizing contact with the glass walls.
And this balance between cohesion and adhesion also explains why mercury forms those neat little spherical balls on a surface.
Right. Strong cohesion pulls it into a sphere to minimize surface area.
While water, with stronger adhesion to glass, tends to spread out more.
Exactly. It's all connected.
Okay, great. Now, to wrap things up, let's quickly touch on heat transfer using this kinetic model. We experience this constantly. The source mentioned conduction and convection.
Right. Two key ways heat moves around.
Conduction first. That's heat moving through something without the material itself moving, like a metal spoon handle getting hot if the end is in soup.
Perfect example. On the molecular level, heating one end gives those atoms more kinetic energy. They vibrate more intensely. They bump into their neighbors, transferring some of that energy. Those neighbors vibrate more, bump into their neighbors.
Like a chain reaction of vibrations passing the heat along.
Exactly. The atoms themselves don't travel down the spoon. They just vibrate more vigorously in their spots, passing the energy along through collisions.
So energy transfer by direct contact and vibration.
Got it. What about convection, then? That sounds like it involves actual movement.
It does. Convection is heat transfer through the actual movement of a heated fluid, so a liquid or a gas.
How does that work?
Well, when you heat a fluid, its molecules gain energy, move faster, spread out a bit. This makes the heated part less dense.
Okay.
And less dense fluids tend to rise. So the warmer, less dense fluid moves upwards, carrying its heat energy with it.
And colder, denser fluid sinks to replace it.
Precisely. Cooler, denser fluid sinks, gets heated, becomes less dense, rises. You get these circular movements called convection currents.
Like how a radiator heats a room, warms the air near it, that air rises, cooler air falls.
That's a perfect example of convection currents in action.
Yeah.
So conduction is like a tiny energy handoff. And convection is like a bulk delivery service where the heated stuff actually moves.
You got it. A really good way to put it.
Wow. This has been a really fantastic deep dive into what matter actually is. We've gone from ancient ideas right through to the kinetic theory and seen how these incredibly tiny, constantly moving particles and the forces between them basically explain the properties of solids, liquids, and gases, and even things like surface tension and heat transfer.
It's pretty amazing when you realize that this seemingly simple idea, tiny moving parts, explains so much, from how perfume spreads out to why insects can walk on water.
Yeah.
It just shows how understanding this invisible world really helps explain the big visible world around us.
Absolutely. So for you listening, maybe think about this. Now that you have this picture of constantly moving atoms and molecules, what else might their behavior be explaining? What other everyday things might suddenly make more sense?
Yeah, what other surprising stuff might be going on at that tiny level? It's a whole hidden reality, really, all based on this fundamental idea of tiny things in constant motion. Lots to think about.